Good morning, everyone. How are you all doing today?
Doing good.
Good to hear. Good to hear. Did everyone sign up for Achieve? Because first, looks like almost everyone did. That's good. First learning curve is due today at the end of the day, and second is due tomorrow. So it'd definitely be a good idea to get on there if you have not. Okay, so I completely spaced over the weekend and totally forgot about the syllabus. I will get that to you today. I actually have time today to work on that. I will get that put together. That shouldn't take too much time. my apologies that I did not have that the section syllabus uploaded with like office hours and that kind of stuff on it. I will get that uploaded today. My apologies. What does my shirt say? So it's so there's it says math is a compact sport. So it's we have a thing called at Penn State called Math Advanced Study Semesters, and so it's like a one semester thing for undergrads where basically they let 3 professors teach whatever the hell they want, which is kind of cool. And then so you get students mostly from Penn State, but that's actually how I my first experience with Penn State was coming here as an undergrad. You also get students from abroad and from other schools come here for a semester, and you just get to learn whatever the hell these professors want to teach, and it's a really cool experience. But we always make a shirt every semester, and it's usually a bunch of dumb inside jokes thrown together. So this is just kind of a mixture of like it involves some of the courses that were taught, and also there's one TA who very infamously would ride a unicycle everywhere. So of course they had to put a unicycle on there somewhere. But yeah, that's it's a bit difficult to explain the rest of it, but yeah, that's basically what it is. A bunch of inside jokes. Okay. Let's get started because I really want to finish off this chapter today. Okay, so we're going to finish up, ideally, talking about chapter 12.2. So 3-dimensional space continued. So last time we talked about just sort of the geometry orientation of R3, points in R3. We talked about distance and spheres. So let's talk about one more very simple surface really, really quickly because we're going to talk about it more in depth later. But let's look at the surface given by the following equation. So let's say x minus 1 squared plus y minus 2 squared is equal to 4, let's say. So I want to emphasize that this is an equation which describes something in R2 as well, right? So if I just gave you this equation and said, what does this describe? Well, it depends, right? So it depends on if we're describing a set of points in R2, right? A set of points x, y, which satisfy this equation, in which case, what would that describe? So if I were in the plane and I gave you this equation, what is this set of points? What type of object?
Circle.
Right, it's a circle centered at the point 1, 2 of radius 2. But in R3, it's a very different object. So you want to be careful about that, because the same equation can describe a different thing depending on whether you're in R2 or R3, et cetera, et cetera. But in R3, let's figure out what this is describing. Okay, so notice the reason there's ambiguity is because this equation doesn't involve z, right? We're looking for the set of points x, y, z, which satisfy this equation. Well, this equation doesn't involve z, so it literally doesn't matter. Let me close the door real quick. It doesn't matter what the z coordinate is. The z coordinate does not affect whether or not a point x, y, z satisfies this equation. So z doesn't matter here. So what we're going to do is we're going to take sort of slices of this. We're going to see what happens for different values of z. And we'll see this later. It's called taking traces. We'll do this later when we talk about more complicated surfaces. But so let's look at what happens in the plane z equals 0. In other words, we're going to intersect the plane z equals 0, which what is the plane z equals 0? It's one of the coordinate planes. Which one? Right, the xy plane. Oh, sorry. That might have been in response to something else. But the plane z equals 0 is the xy plane. So we're going to intersect that plane with our surface and see what we get, and then intersect other planes with that, see what we get, and sort of put everything together. So the xy plane, the plane z equals 0. So we're going to look at the set of points x, y, 0, which satisfy that. Well, basically, this is the xy plane, right? So if we forget about z, we know this is just the circle of radius 2 in the plane. Oh, sorry. Centered at the point 1, 2, 0. So we get that circle and the plane z equals 0. And similarly, if we look at z equals 1, and we think of this as a plane parallel to the xy plane, well, you look down on it, you're going to get the exact same thing, right? You get that same circle, except it's going to be centered at the point. Sorry. Centered at the point 1, 2. Now z is 1. So you're going to get a circle in that plane centered at the point 1, 2, 1 of radius 2. And then do the same for z equals 2, z equals 3, et cetera. You're going to get a bunch of these same copies of that circle, just translated up And when you put all these together, you let Z be whatever, you're just going to get a cylinder. So it's a cylinder. It's basically a bunch of these circles centered at points 1, 2, and Z can be whatever, right? That's going to describe some vertical line. That's the center of our cylinder. It's got radius 2. So what this equation describes is cylinder with sort of the axis of symmetry, which is going to be the vertical line through the point 1, 2, 0. And the cylinder is going to have radius 2. I just want to describe this. I went really quickly through that, but just for the sake of homework, I want to describe that. We'll go over it in more detail later. It's if you need to look back at the book or something to understand that, that's fine. But I just wanted to go through that really quickly. But any questions about that, because it's not super duper important, but I did want to mention it. No, so what I was doing was I was describing a way we can figure out what this surface is. So what we're doing is basically we're just intersecting. That's a way we are going to sort of visualize more complicated surfaces, is we're going to intersect those surfaces with planes parallel to the coordinate planes. And then we're going to see what curves we get when we intersect them, right? So when we intersect whatever this is, we don't know what it is yet. With the plane Z equals 0, the XY plane, we just get a circle in the XY plane centered at the point 1, 2, 0. When we intersect it with, say, the plane Z equals 1, we get basically the same circle, just translated up, centered at the point 1, 2, 1. And then we play the same game. You intersect it with any plane, Z equals something, right? Those are all going to be planes parallel to the XY plane. You're going to get the same circle, just translated to Z equals whatever you had. And when you put all those together, you get this cylinder here, if that makes sense. Would you add? No, okay, so that it's kind of hard to describe the logic right now of why I chose to intersect the plane Z equals 0 with it, but Z is not involved in the equation. Which is why I chose it, but it would take a bit of time to explain that. Like I said, we'll talk in more detail about it later. But yeah. We'll just leave it at that for now. My apologies if that's a little confusing, but gotta move along here. Okay, really super quickly, because it's basically nothing new. We looked at vectors in the plane. Now let's look at vectors in space. Turns out basically nothing, exactly the same rules apply. So vectors in the plane, right? Remember, a vector has magnitude and a direction. Well, a vector in the plane the direction can be described. The direction points in 2 dimensions, right? So like you could describe a 2-dimensional vector by thinking about like north, south, east, west, right? So you could have a vector pointing directly east, northeast, etc. Those are 2-dimensional vectors. You can describe their direction using 2 dimensions and the plane. Vectors in R3 you need 3 dimensions to describe the direction. Basically, just think of them as arrows in R3. All right, so if you just said, in order to describe the direction of a vector here, like you could say north pointing like upwards by whatever degrees or something like that. That's maybe a bad example. But yeah, just think arrows in R3 for vectors in R3 here. And all the same rules apply, right? So similarly to an R2, we can represent them geometrically as arrows, or we can represent them sort of algebraically in component form. So if we have a point ABC in R3, we can look at the vector which starts at the origin and ends at this point. Right, so O is the origin. So the vector which starts at the origin ends at the point ABC, which we'll call P. We do the same thing. We call that the vector ABC. So the position, the vector ABC is the position vector for the point ABC. Remember, position vector for a point is just a vector which starts at the origin and ends at that point. But a point and a vector are 2 different things. And so we need to use different notation for the 2. We use the triangular brackets for the vector and the round parentheses for the point. But vectors in R3 have 3 components, right? You have an X, Y, and a Z component. And that tells you how far in the X direction our vector goes, how far in the Y direction our vector goes, and how far in the Z direction our vector goes. So we have our X component, our Y component, and our Z component of our vector. So if we have a vector ABC, the magnitude of our vector, remember, it's just going to be the length of that arrow, which starts at the point 0, ends at the point ABC. Using the distance formula, we get the same thing, right? It's just the square root of the sum of the components squared. So square root A squared plus B squared plus C squared. And it's not even worth mentioning because it's all exactly the same as before, but all the vector algebra works the same way, right? You add two vectors together, ABC plus DEF, you're adding component by component, right? You add the first components together, you add the second components together, you add the third components together. That's your new vector. So you add vectors together component by component. Multiplication by a scalar does the same thing. You multiply each component by the scalar. And I want to remind you, because we'll use this in just a second when we talk about lines. But if we have two vectors v and w, oops, they are parallel. Let me say this holds for non-zero vectors. We also have the zero vector in R3, of course. It's a vector which starts and ends at the same point. That's the vector 0, 0, 0. But if we have two, and that doesn't have a direction, similarly. But if we have two non-zero vectors, they're parallel if and only if they're scalar multiples of each other. So if W is lambda times the other vector, for some scalar lambda. So this is our vector v. If you multiply it by a scalar, remember the absolute value of the scalar tells you how much you're stretching the length of this guy. And if it's positive, the scalar, you get a vector pointing in the same direction. And if it's negative, you get a vector pointing in the exact opposite direction. So if you multiply a vector by a scalar, you get something either pointing in the same direction or the exact opposite direction. Both of those are parallel. Similarly, if you have, for the same reason, some vector, which is just a multiple of your vector, then it's going to be parallel. Right. So if we have like -2 times v, you get a vector twice as long. Absolute value of -2 is 2, and pointing in the opposite direction because it's negative. And so similarly, yeah, you take any vector, you multiply it by some scalar. It's either going to point in the same direction or it's going to point in the opposite direction. But in every case, you get a parallel vector. So you're going to be looking at curves in R3. And we're going to be using the language of vectors because it's very convenient to do calculus with these, as we'll see. In addition, and all sorts of algebraic operations that you can't do on points. It's very nice. So here's how we're usually going to think about curves in R3. So Suppose we have some curve C in R3. What we want to do is we want to describe all the points X, Y, Z, which lie on this curve. So what we're going to do is we're going to pretend we're a particle. Say we're a particle right here. So we have a particle on a curve, and we're moving along this curve in space. So we're moving, so at different times, t, we're at different points along the curve. So what we're going to do is we're going to say, okay, what is the x coordinate of our curve at time t? What is the y coordinate of our curve at time t? What is the z coordinate? What is the z coordinate of our particle at time t? So at some time t, our particle is at the point x of t, that's the x coordinate at time t, y of t, y coordinate at time t, and z of t. Sorry, that's kind of sloppy there, but that is the point our particle is on the curve at time t. And those are all functions, right? If you take a different time t, the x, y, and z coordinates are going to be different, right? So each of those are functions of t, and they tell you what the x, y, and z coordinates are at time t. And you put them together, those give you some point on the curve at time t. So rather than using points, we're going to use the position vectors for those points. So think about the vector which starts at the origin and ends at that point, x of t, y of t, z of t. Right, if it starts at the origin, ends at x of t, y of t, z of t, we get the point, or sorry, we get the vector x of t, y of t, z of t. So that's the position vector for the particle at time t. And we're going to use vectors because there's a lot of nice algebraic and calculus properties of vectors that we're going to leverage later to talk about these curves. But basically, we're going to sort of use points on the curve and vectors and the position vectors for these points on the curve interchangeably, right? What we're interested in are the points on this curve, but for algebraic reasons, we're going to use the position vectors for those points. The vectors which start at the origin, end on our curve. So at time t, the vector r of t ends at a point over here on the curve. For some other time t, we get a vector which ends at some other point on the curve, so on and so forth. So we're going to get a bunch of vectors which start at the origin, end at points on our curve. And we think of a particle as moving along this curve. And we'll talk more about that later as well. But any questions about that? This is how we're going to be describing curves. We're going to use these vector equations, right? We're going to give vectors, each of whose components are functions of t. And they tell you basically the x coordinate, y coordinate, and z coordinate of a particle on your curve at time t. But yeah, each of these vectors, they're vectors starting at the origin, ending at some point on the curve. And as you vary t, these vectors are going to trace out your space curve. So the simplest curve you could have is a straight line. So let's look at the equation of lines here. So in R2, we can completely describe a line with two pieces of information. So we need a point on the line. So some point we know is on the line. Could be the y-intercept, could be an x-intercept, could just be some random point we know. So we know the point P naught, say, on our line. And we need to know the slope of the line. But if we know a point on the line and we know the slope of the line, then we know exactly what line we're talking about. We can get an equation for the line. All right, you can just use point slope form to get an equation of the line. But if you know a point, you know the slope. There's only one line which has that point and has that slope on the line. And you can write the equation of that line. But remember, so slope is just rise over run, right? So the vertical change over the horizontal change. So in R3, situation is basically exactly the same, except slope doesn't make sense in R3, right? So maybe you could define rise as like change in z, but then what is run, right? You have x and y to deal with. So in R3, if instead of just thinking about slope, we think about like the direction of the line, like think of a parallel vector to our curve here. That tells us the direction our line is going. And so if we know a point on the line and we know the direction our line points, there's only one line which goes through that point in that direction, right? That's something we can use in R3. So in R3, if you want the equation of a line, you need to know a point on the line, and you need to know the direction of the line, or in other words, a vector which is parallel to the line. So in other words, you need to know a vector which is parallel to your line. So there's our line L. But if you know those two things, then you know exactly what line you're talking about. You can write the equation of that line. And I want to emphasize this because on questions that are asking you to find the equation of a line, those are the two things you're always going to try to find. You're not going to be given them directly usually, but you need to find a point on your line. You need to find a direction, a parallel vector for your line. So let's find an equation for a line in R3, which goes through some given point and is parallel to some given vector. So suppose we know a given point, P naught, on our line. We know a point on our line. So we're going to do like we did, like we talked about here. Instead of describing the points on the line, we're going to look at position vectors. So vectors which start at the origin end on our line. So we're going to describe all these vectors. Well, we know one vector already because we know a point on the line. So R naught is going to be the position vector. For our given point, P naught. Clearly that ends on the line because we know that vector is on the line. So we also know a parallel vector to our line. So we have a vector V, which is parallel to our line. So it's parallel to our line. So basically, so think about it as if you're on your line, right? Say we're at the point P naught, and we walk in the direction of V, right? That means we're walking along our line because we're walking parallel to our line. Start on our line, you walk parallel to your line, you're going to stay on the line. So if you do R naught, and then you do the vector V, hang on, let me. You're going to end at another point on your line, right? Because you started on your line and you walk parallel to your line. That's also going to be on your line. And that's true for any vector parallel to your line, right? You start on the line, you walk in a direction parallel to your line, you're going to stay on the line. And we know all the vectors parallel to our line are just scalar multiples of this vector V, right? So basically, you just do R naught, and then you do some scalar multiple of the vector V. You're going to be tracing out the line, right? If t is negative, you're going to be going the opposite direction along the line. If t is positive, you're going to be going in the direction of v along the line at varying lengths. And every point on the line is just, you do the vector r naught, that gets you your known point, and then you go some direction in the direction of v. All of those guys are described by this equation. So this is the vector equation for the line through P naught. So our point P naught has position vector R naught. That's our R naught here. And the parallel direction we have for our line is the vector v. So you do R naught, the position vector for your known point, plus t times your parallel vector v. And as you let t vary from negative infinity to positive infinity, you're going to trace out your entire line. Yeah, that's a vector times t. T is just going to be a scalar, a number. So if P naught is your point x naught, y naught, z naught, and your parallel vector is ABC, your equation becomes, so it's the point, it's R naught, so you get the vector x naught, y naught, z naught, the position vector for your known point, plus t times the vector v, which is the vector ABC. So that's the vector equation for the line through the point x naught, y naught, z naught, right? There's our known point, parallel to the vector ABC. So the stuff multiplied by t is the parallel vector. The thing by itself is the known point. So this is useful, but we're more often going to write it slightly differently. So if we think of R of t, oh, no, don't do that, don't do that, don't do that. Come on. There we go. So R of t is going to describe our points on our line, right? X of t, y of t, z of t. So we have a vector on the left-hand side. We have a vector on the right-hand side. If we write that as a single vector, right? We bring our t inside the vector and then add the two component by component. We get we know two vectors are equal if and only their components are equal, right? So the first component of the left-hand side is x of t. First component of the right-hand side is x naught plus t times a, or a times t. And then equating the second components, this is a separate equation. So we get y of t is equal to y naught, the y coordinate of the known point, plus b times t. And then equating the z components, we get z naught plus c times t. So these are the parametric equations for the line through the known point x naught, y naught, z naught, right? So the stuff not multiplied by t gives you the coordinates of the known point. And the stuff multiplied by t, the ABC, give you the components of the parallel vector. And usually unstated, but t is allowed to vary between negative infinity and positive infinity. Stop it. Okay. So let's do a quick example. Find the equation of a line. And we're not specifically going to be given a direction and a point, but we're going to need to find that, and then we're going to use that info to find the equation of the line. So let's find the equation of the line through the points P, which is the point 1, 0, 2, and the point Q, which is the point 2, 5, negative 1. Okay. So anytime you need to find the equation of a line, you need to find two things: a point, and you need to find a parallel vector. If you can find those two things, you can write the equation. But every time you get one of these problems, those are the two things you try to find. So I'm not going to pretend like these are actually the points here, but let's just, for the sake of argument, say this is our line, want to find the equation of it. We know 2 points on it. Well, how do we do it? Okay, so point is easy. We're given 2 points. Just pick one of them. P is fine. Q is also fine, but let's just pick P here. So we'll pick the point 1, 0, 2, which we know is on our line. Now we're not given a parallel vector, but how do we get a parallel vector here? We're given 2 points. What's a vector related to those 2 points, which happens to be parallel to our line? Right, so here's a point P, here's a point Q. What about the vector which starts at P and ends at Q? Right, that's clearly parallel to our vector, right? So that works just fine. And in fact, that's how you're going to answer these questions, is you're going to look at the vector which starts at P and ends at Q, or the other vector, QP, is fine also. So what is the vector PQ? Well, remember, think of a vector as where you started, component by component, where you ended minus where you started, right? So for the first component, we started at 2, or we ended at 2, we started at 1. So we've gone from 1 to 2, we've increased by 1, right? So the first component is 2 minus 1, it's 1. What's the second component of the vector PQ?
5.
Right, we've gone from 0 to 5. Second component is 5. And the third component, we've gone from 2 to -1. We've decreased by 3. So we get -3. So we have a point. We have a parallel vector. And so let's write it in scalar parametric form. X of t is the x coordinate of the known point, which is 1, plus t times the x component of the parallel vector, which is 1. So 1 plus 1 times t, 1 plus t. Y of t is going to be the y component, or the y coordinate of the known point, 0. I'll just write it 0. Plus t times the y component of our parallel vector. So 0 plus 5t. And z of t, is going to be the z coordinate of the known point, 2, plus t times -3, the z component of our point. So 2 minus 3t. And those are the scalar parametric equations for the line through 1, 0, 2 and 2, 5, -1. Okay, so I've already gone over a few minutes. If you need to leave, please go do so. I will post this lecture on YouTube, but I don't want to start the semester in a hole behind. So I'm going to go ahead and quickly finish up this stuff. And if you can hang around, that's fine. If you need to go, that's fine. Then you can watch the lecture later. I don't want to make a habit of this, but I do not want to get behind. So my apologies. But I'm gonna finish up the rest of the chapter. Could you have also used the point Q for the equations? Yes, that's a good question, and that you absolutely could. And that is an important point that I want to mention. And that is, equations for lines are not unique. Right, you can have two different equations which describe the same line. Why is that? Well, that is because, oh my God, dude, stop it. That is because your equation depends on the point you pick, and you can pick any point you want on the line. So for instance, in the last equation, we picked the point 1, 0, 2, but we could also just pick 2, 5, -1. And then you would replace this 1, 0, 2 with 2, 5, -1. And you would have a different equation, but it would still describe the same line. You just picked a different point on there, but it's still the same set of points that this is describing. So you can get a different equation by picking a different point. You can also get a different equation by picking a different parallel vector, right? So if a vector v is parallel to your line, so is any multiple of v. So is like -2 times v. That's parallel to V, so it's parallel to the line also. That's going to change the equation, right? If instead of PQ, we picked the vector QV or QP, it points in the opposite direction, but it's still parallel to our line, right? And we would have gotten 1 minus t, negative 5t to plus 3t. Different equation, but it still describes the same line. So that's something to keep in mind. So there are many correct equations for a given line, right? Picking different points, picking different parallel vectors will give you different equations, but they all describe the same line. Also, I want to mention, so if we let t go from negative infinity to positive infinity, we're tracing out the entire line, right? So this line contains the points P and Q, but it goes infinitely in both directions. And if you let t go from negative infinity to positive infinity, you get the entire line. But sometimes we just want the line segment with endpoints P and Q. So line segment from a point P to a point Q. It's a piece of a whole line, but we only want the bits between P and Q. So that's easy to do. So it's the same thing, except we're just restricting the values of t we can take. So if R naught is a position vector for our point P, so suppose we start at the point P, we end at the point Q. Suppose R1 is a position vector for our point Q. So the equation for the line segment is just R naught plus T times R1 minus R naught. So here's R naught. And if you remember, R1 minus R naught, vector subtraction, if you start the two vectors at the same point, R1 minus R naught is a vector which starts at the negative guy, ends at the positive guy. So that's a vector R1 minus R naught. And here we're just going to let t go from 0 to 1. And that's, so it's because, so what's going to happen is, think of it this way. So when t is equal to 0, so at time 0, you start at the point P, right? So in this equation, when t is equal to 0, you have r naught plus 0 times a vector. You just get the vector r naught. So you start here at time 0. And you're going to be traveling in the direction of r1 minus r naught. And so as you go from 0 to 1, you get longer and longer vectors until you hit the vector r1 minus r naught at time 1. So when you plug in t equals 1 here, you get r naught plus r1 minus r naught. So r naught plus r1 minus r naught, the r naughts cancel, and you're just left with the vector r1. And so, yeah, you do r naught here. That's where you start. And at time 1, you do r naught and then r1 minus r naught and end here. And for t between 0 and 1, you're just moving in this direction until you hit t equals 1. Yeah, I don't want to dwell on that too long, but it's really easy to do these line segments because t always goes from 0 to 1 if you set it up in this way, right? If you start at p, you end at q. You let your direction vector be the vector from p to q. You let your known point be p, where you start, and you just write the vector equation of the line, but you restrict t to go from 0 to 1. It's always going to work this way if you let your parallel vector be the vector from p to q. Does that make sense? Any questions about that? Okay, and then I want to end by looking at how to tell if two lines intersect in R3. Okay, so in R2, life is simple. Either two lines are parallel and they never intersect, or they're the same line and they intersect in infinitely many places. They're parallel. But if two lines are not the same line, either they're parallel and they don't intersect. Oops. Or they're not parallel and they intersect somewhere. If two lines are not parallel, they are always going to intersect at some point in R2. In R3, we have one more dimension we can move. And so two non-parallel lines could also not intersect, right? So two parallel lines are obviously not going to intersect if they're not the same line. But you could have two lines in R3 which are not parallel, which never intersect. So imagine you have some line in the plane z equals 0. Suppose a line is entirely in the xy plane, and then some line in z equals 1. Those two lines can never share a point because every point down here, the z coordinate is 0. Every point up here, the z coordinate is 1. They're never going to intersect, but they might not be parallel. So those are called skew lines. Oh, and I guess I didn't mention this, but We say two lines are parallel if, well, we don't say, but two lines are parallel if their direction vectors are parallel. Right, so suppose we have two different lines. Suppose our first line is given by x naught is equal to 2 minus 3t, y naught is equal to t, and z naught is equal to, let's say 3. And let's say our second line is, let's say, 1 plus 6t, negative 1 minus 2t, and let's say 3. Z is equal to 3. How do we know if these two lines are parallel? Well, we look at the direction vectors. So remember, the components of the direction vector are the stuff multiplied by t in our equations. So the x component of our direction vector for our first guy is negative 3. The y component is 1. And what's the z component of our direction vector for the first line? 0. So that's a direction vector for our first line. Let's say that's v1. What's the direction vector for our second line?
Six, negative 2, and 0.
Right, so 6, negative 2, 0. So the direction vector for our first is negative 3, 1, 0. Direction vector for our second is 6, negative 2, 0. Are these parallel vectors? In other words, are they scalar multiples of each other?
Yes.
Yes, right? 6, negative 2, 0 is negative 2 times v1. So these guys are parallel because the direction vectors are parallel. Because they're scalar multiples of each other, the direction vectors. But if they're not, then you're not parallel. Yes, sure.
Will it always be that easy to see if they are if the direction vectors are multiples of each other?
Yeah, so if you have the equations, you can just eyeball the equations. If you don't have the equations, then you're going to have to get the equations. And then once you have the equations, though, you can look at it and tell if you're parallel by just figuring out what the direction vectors are for the two and seeing if they're multiples of each other. Yeah. Okay. Okay, so if you have two lines which are not parallel, the direction vectors are not scalar multiples of each other in R3, either they intersect at a single point or they don't intersect and they're called skew. So in other words, they don't intersect. So either they intersect at one point or they don't intersect at all. They're skew lines. So with that in mind, let's see. I'll give you the equation of two lines and let's see if they intersect. So our first line is going to be given by 101 plus t times 335. And our second line is going to be given by 361 plus t times the vector 4, -27. Okay. So here's the way you want to think about it. So the way here's an important sort of way to think about these equations of lines. We'll call them parameterizations later, but these equations for the lines. The way we get points on a line, one way to think of it is, so we're thinking about this as a particle traveling along our line, as time goes from negative infinity to positive infinity. So the way we get some point on a line is you can plug in a value of t, right? You plug in some value of t, that tells you where your particle is on your line at time t. So if our two lines intersect, suppose they do intersect, right? So that means we have a point which lies on both lines, a single point. That means if I'm a particle on line 1, I'm going to be at that point at some time t1. So in other words, are there times t1 and t2 where at time t1, I'm at this point on the first line, and at some other time t2, I'm at that same point on the second line. So can I find two times where at the first time I'm at that point on the first line, and at the second time t2, I'm at that exact same point on the second line? So if my two lines intersect, there are two times that we can find where I'm at some point on the first line and some other time where I'm at the exact same point on the second line. If the two lines intersect, that is the case. Does everyone understand that bit? It doesn't have to be the same time that you're at that point, but there have to be two times where at that time I'm on a point of intersection on the first line, and at some other time I'm at that point of intersection on the second line. Right, so two times T1 and T2 that satisfy this equation. Plug in T1 into the first, plug in T2 into the second, and we get the same vector, right? The same position vector for the same point on both lines. So let's write down what that means in vector form. So when I plug in T1 on my first line, so I get 101 plus T1 times 335. So that's T1 times that. And then I plug in T2 in the second, and I get 361 plus T2 times 4 negative 27. 4 negative 27. And so we have a vector on the left, a vector on the right. Let's write them both as single vectors and then equate their components. So writing the left-hand side as a single vector, so bringing the T1 inside the second vector, adding component by component, I get 1 plus 3t, 0 plus 3t, which is just 3t, sorry, T1. And then 1 plus 5 times T1. On the left-hand side. And doing the same for the right-hand side, I get 3 plus 4 times T2, 6 minus 2 times T2, and 1 plus 7 times T2. So then, finding out whether they intersect comes down to figuring out if there's some T1 and some T2 satisfying this equation. Well, we have two vectors. They're equal if and only if each component is equal. So we have actually three equations in our two unknowns, T1 and T2. So let's write those three equations down. So first components, 1 plus 3t1 equals 3 plus 4t2. Sorry, nope, 3 plus 4, no. And then equation our second components, we get 3t1 equals 6 minus 2t2. Uh, 6 minus 2t2. And then equating the third components, 1 plus 5t1 equals 1 plus 7t2. So if the lines intersect, We can find a T1 and a T2 which satisfy all these at the same time. But if we can't find a T1 and a T2 which satisfy all three at the same time, the lines don't intersect. So sort of for this one, actually, there's going to be a nice shortcut. But how you're normally going to go about this is basically, so we have two unknowns. So pick two of the equations. You have two equations and two unknowns, two linear equations and two unknowns. You can solve for T1 and T2. You will have a T1 and a T2 which satisfy two of these equations at the same time. Then you're going to plug in that value of T1 and T2 into the third equation. And see if it's satisfied, see if it's true. If it is, then you found a T1 and a T2 which satisfy all three equations, the lines intersect. If it's not, then the lines are skewed. They don't intersect. So in the book, they go through this. So they pick the first two equations. You find out T1 has to be 14 over 9. T2 has to be 2 over 3. If they intersect. So then we plug this into the third equation. We see if the z coordinates match up. We see that they don't, in fact. When you plug it into the third equation, the equation's not satisfied. So the two lines don't intersect. And that takes a bit of time to show. But in fact, there's a nice shortcut here. And that's because we can look at the third equation. 1 plus 5t1 equals 1 plus 7t2. What are the only values of t1 and t2 which satisfy the third equation? They both have to be 0, right? Because 1 plus 5 times something equals 1 plus 7 times something. Well, both of those things have to be 0. That's the only time that's true, right? So if the two intersect, T1 and T2 have to be 0, but that clearly doesn't satisfy the other equations. So the two lines don't intersect. Right. There's no time T1 where on the first line we're at some point, and at another time on the second line we're at the same point. Right. We can never make all the coordinates match up for some time T1 and on the first and sometime T2 on the second. But that's it's usually not going to be that easy, what I just described. Usually you're going to have to pick two equations, solve for T1 and T2, and then plug them into the third equation and see if they match up. Any questions about this example?
Would you mind actually going through the steps?
Okay, so we have
That takes much.
we want to know if they intersect. So what it means if two lines intersect, it means they share a point, right? So if they share a point, well, there's some time T1 that on the first line we're at that point, the point of intersection. And then there's some other time T2 where on the second line we're at the same point. So what we want to do is we want to see if there's some time T1 where when we plug it into the first equation, we get the same vector as when we plug in some other time t2 into the second equation, right? We want to see if this holds here. Can we find a t1 and a t2 where we get the same point on both lines? And so what we do is we plug in t1 into the first equation, t2 into the second equation. That's what we do here. We write them as single vectors. That's what we do here. We have a vector equals a vector. That's only true if each component is the same. So that means the first components we set them equal to each other. The second components, we set them equal to each other. The third components, we set them equal to each other. That gives us 3 equations in 2 unknowns, T1 and T2. So that's too many equations because you can solve for T1 and T2 if you have 2 equations and 2 unknowns, but we have 3 equations. So what we do is we pick 2 of the equations, just pick the first and second, solve for T1 and T2. So there is going to be a T1 and a T2, barring some circumstances, but there's going to be a T1 and T2, which satisfies the first 2 equations, right? So that means the X and Y coordinates are the same at some point. And so then we plug those into the third equation, the ones we got from the first 2, and see if the Z coordinates also match up. If they do, then we have a point of intersection, the 2 lines intersect. If for those T1 and T2 though, the third equation does not match up, that means our lines never intersect, so they're skewed. Substitution, yeah, you would just do substitution and elimination, right? Same way you always do to solve a system of linear equations. Exactly, Terrell, yeah. Any other questions? Yes, you could use matrices. You could use matrices. Matrices are just a different way of organizing your information, but yeah, you're doing the same thing. Yeah. Okay, so I went way over. My apologies. But we're caught up, and I will make sure to stay on top of things and not go over in the future. All right, so have a great rest of your day. I will see you guys on Wednesday. So first learning curve for 12.1 is due at the end of the day. Learning curve for this chapter is due by the end of tomorrow. And yeah, I'll see you guys on Wednesday, and I will send out the, I'll post the syllabus by the end of today. Have a good one, guys.
Thank you.